this lecture, I'd like to talk to you about enolate formation, and we're going to look specifically at kinetic versus thermodynamic enolates. So if we look at the ketone down here below, we have two potential alpha positions. So we'll circle this position right here, and we'll just call this pathway number 2, and this is our number 2 approach down that way. And then we'll take a look at this guy right here, and we'll call that pathway number 1, and then this will be our number 1 pathway this direction. Now, if we take a look at what happens at pathway number 1, our base is coming over and deprotonating one of our H's at this position, right? So we kind of have our H atom up here. We're going to swing around, grab that H, and do this. Now, what that's going to give us here is a CH2 minus. And of course, this has resonance to give us that, right? And then that would give us an oxygen with a negative charge on it. All right, now we'll look at this little notation here that I've boxed in just a second. So, but that's the first possibility. The second possibility is that our H from over here gets pulled off, right, with our base. To do that, that would give us a negative charge at this tertiary position, and then we would have, again, another resonance structure here with the oxygen bearing the burden of that negative charge. Now, when we look at these two outcomes, we can see that this position is easier to access. It's more accessible to our base. So because of that, we have more of a chance of deprotonating here simply because of sterics. So because of that, it results in this being deprotonated faster. You can imagine that. Now, this position down here is more sterically hindered, so it's a little bit slower to respond. But what we get here is a set of resonance structures in which, when we look at it, when we look at all 4 of these resonance structures, this is the most stable enolate. Negative charge on oxygen, that's a good thing. Carbon-carbon double bond, maximally substituted, that's a good thing. So that's the most stable. So the most stable enolate is going to lead to the product that is more thermodynamically stable. So we call this the thermodynamic product. Now, the enolate that's most easily forms the fastest, and therefore we call that the kinetic product. Now, there's more involved here. Okay, let's take a look at this ketone here. This ketone, as we saw before, has 2 positions in which we can do a deprotonation. If we deprotonate over here on our left-hand side, our negative charge ends up at this position, and through pushing electrons at this spot up to our oxygen, we get this other resonance form of our enolate. This red H that's here can also get lost, and when that happens, it puts a negative charge at this position, right, at the carbon that H was attached to, and through pushing electrons, making a double bond here, moving those up to our oxygen, we get this resonance structure. Now, if we compare this set of enolates with this set of enolates down below, we can make some comments. The first thing that we can say is that this H is probably easier to lose since it's not nested kind of between these 2 methyl groups. So it's more accessible, right? So if it's more accessible, then it should be able to be deprotonated at a faster rate. The other thing we can say is that if this H is lost, right, this red H, if we come down here, that this resultant resonance form is a more substituted double bond, and therefore that's probably the most stable resonance structure of all of our enolates, so it's more stable. So we get a more stable enolate down here and a less stable enolate up here. It's less stable, but it also has a more accessible hydrogen atom, which is going to come back later, and we'll end up designating it with a special name. Now, we can take a look at all of these things and remove some arrows, and we can also discuss this phenomena when we look at reaction energy diagrams. So let's see how things shuffle around here. Less stable enolate moved over to the left-hand side, more stable on the right-hand side, and the original ketone hanging out down here at the bottom. So what we can do is we can plot energies. So moving over to the left, we have a reaction energy profile here, an energy curve, coming over to form our less stable enolate. Now, since this forms faster, we're going to call it the kinetic enolate. And we said that forms faster because that H is more accessible. We'll see there's other reasons why in just a second too. So we get this activation energy here. We can go over to the right-hand side too, right? And we can become this more stable enolate when we get that double bond here. That was the most stable of our enolate resonance structures. Because it was the most stable, we call it the thermodynamically stable enolate, or sometimes just the thermodynamic enolate. And it has its own activation energy also. Now, if we look over to the left, there's a few things we can point out. So that H that was lost, this position here, it's less sterically hindered. And because of that, there's a lower barrier to remove that H atom. And that gives us a lower activation energy, which means that it forms faster. Now, in order for us to favor the formation of this, we require special reaction conditions. We want the conditions to be irreversible. And to do that, we need to use a base that's really, really strong and also a little bit sterically hindered to prevent the attack at this position. So we use lithium diisopropyl amide. We'll look at that structure in just a second. Moving over here to our right-hand side, that H is more sterically hindered, right? It's more crowded. It has a higher barrier to remove that H atom, and because of that, it's formed slower because it has a higher activation energy, right? And in order for us to form this, we have to have conditions that are reversible. So what happens under reversible conditions is we use something like an alkoxide. And under reversible conditions, our original ketone can come over here and form the kinetic enolate. But because we're under reversible conditions, this thing can pop back over to become our uncharged kind of ketone again, right? And then we can swing up over here and we come down to a lower energy and we form the more stable enolate, which then can react. But because we're reversible, we can always, right, shift and kind of move between the less stable enolate and the more stable enolate. Now, looking at this, we can see that there's an energy difference between our less stable enolate here, right, moving down our more stable enolate over here. Now, the energy difference here is dependent on the degree of stability between the kinetic enolate and the thermodynamic enolate. So if you're more stable over here compared to the less stable enolate, that difference can change depending on circumstances. Then that number here, that gap, can get larger and larger. All right, now the conditions we'll use for favoring the thermodynamic product are going to be using alkoxides as bases. So hydroxides or alkoxides are the key to this. So when we look at our ketone down here below, right, we have this alpha 1 position, we have this alpha 2 position. The pK of those positions is somewhere around 20-ish or so. And here we have an alkoxide. And just for the sake of looking at this, let's just deprotonate at alpha 2. Of course, alpha 1 can occur also. So then we form over here, we form our enolate. And so we'll write plus resonance, but here's your enolate. And then we get our alcohol. Now alcohols have pKa's ranging from about 15.5 or 7 up to about 18. Right, so you go from water up to a tert-butyl alcohol. So then the KQ for this reaction is going to be equal to 10 raised to the difference of those pKa's. So it's product acid, so we'll call that maybe 17, just to pick a number that falls somewhere between that, right? Minus 20. So the KEQ for this is equal to 10 to the minus 3, right? This is 1 over 1,000. All right, so what that means is that, right, we fall within that realm of being near equilibrium. So we're close here to equilibrium. Okay, so that coupled with a high temperature will lead to the thermoenolate. Well, what if we want to have irreversible conditions? So irreversible is the other side of that coin. So when we look down here below for this, here we want to use the base that's very, very strong. So what we're going to use is we're going to use lithium diisopropyl amide. So there's a couple of different ways that that's prepared. I want to show you just down here below a little bit about this. So here you have HN and then IPR2. So that's diisopropylamine. Right. And to this we can add a base like N-butyl lithium. And that's a very dangerous chemical to work with. It just requires that you be trained in how to use it correctly. Right. Now this can react, and when it does, you would form your nitrogen. Right, it has one lone pair on it. It's going to have 2 with an IPR on there, and that'll give you a negative charge. And then you have the lithium ion, and then you have butane. So when you look at this and you think about, well, how favorable is this reaction? So the pKa of that, somewhere around 36. The pKa of this, around 50. So then the KEQ for this reaction is 10, right, to the 50 minus 36. Right, so you get 10 to the 14. So you greatly favor your products on that. Okay, so a couple things with that. This is your LDA, and it is a strong base, but also it has steric hindrance, right? So the nitrogens here and those isopropyl groups are hanging off of that, and those are big R groups that provide sterics in our base for deprotonating parts of the molecule easier than other parts. All right, so looking back at our reaction up here again, here you have your alpha 1, you have your alpha 2 on here. Here's your LDA, right? So with your LDA, you're going to be deprotonating over on the alpha 1 position more easily here. All right, so that'll lead you down the line to forming your kinetic product, right? And again, we kind of talked about how that bounces around, so it goes directly to the kinetic, and then that would react further to form your final product. It's just the formation of that enolate is the key point that we're looking at here.